Hello, welcome back. Today we're going to talk about slope fields and their applications. If we look at this map of the US, these arrows represent wind vectors. So that's why they have these little arrows on them. Notice they point in a certain direction. So let's say a leaf were to be placed on the panhandle of Oklahoma, like let's say right about here. Whoops, hold on, here, wrong color. Right about here. We want to know in which direction would that leaf travel. Well, if you look at the arrows, notice the direction of all the arrows. They would follow those arrows. And as we move across, it's going to kind of change directions a little bit due to the direction of the wind. And we can almost kind of plot the path of that little leaf as it leaves. Looks like Georgia. That's what we're talking about today. Today we are talking about slope fields, and this is exactly what slope fields do for us. For example, let's say instead of leaving in Oklahoma, let's say we start off a little bit north, right about here. Again, what path would it take? Well, it would start off in the same path, but as we keep moving, look, the wind directions are changing. And if you notice, it's almost exactly the same direction. It looks almost the same direction as it was before, but just slightly more north. That's exactly what slope fields do for us. So they give us the direction that a path travels, or in our case, a function will go. This is what we call a slope field. Now, this is really technically called a vector field, and that's because they have arrows, but we'll talk about the difference more about that in multivariable calculus. I do have a video on that if you want to take a look at my multivariable channel. So a slope field is a graphical technique that we use to describe what a function looks like. The graph of a slope, to graph a slope field, we look at how the function is changing over time. This is what we call a differential equation. And you might recall earlier this year, when we talk about anything about changing, we're in calculus, we call that a derivative or a rate of change. So if I know how a function is changing over time, I can determine exactly the path it's going to make. So let's try practice drawing a slope field, and it is one of the easiest things we do. I'm not going to say it's the most exciting thing we do, but it's pretty easy. So let's take a look at this first example. We are told dy dx equals x minus 1. Well, remember that this does give me the slope. It is a derivative, the slopes. So I'm just going to pick a bunch of points. For example, let's say if I pick the point negative 3, positive 2. I want to find the slope at this point right here. I can do that by plugging in my x value. And it says just negative 3 minus 1. And that's just negative 4. So let me erase that little part right there. And we can draw a slope of like negative 4. Now we're all in pretty luck because since I'm only dealing with the x's, anytime x is negative 3, the slope is just going to be negative 4. They don't always work out this nice, but I can see this, negative 4, negative 4, negative 4, negative 4. What about when x is negative 2? For example, here, where x is negative 2, what would that slope be? Well, up here, my rule says it'd be negative 2 minus 1, which is a negative 3. Doesn't have to be perfect, but you want to make it slightly less. Negative 3, negative 3, negative 3, negative 3, negative 3. And I can keep going at x equals negative 1. It's just going to be negative 2. Again, slightly less steep. Negative 2, negative 2, negative 2. Now, before we move on any further, notice over up here, we had these little arrows. You might see on the map of the US, we have these arrows. But down here, we don't have any arrows. So a slope field has no arrows. Again, if it does have arrows, it's more technically called a vector field because it's going to give us direction. Here, we have no arrows, so we can go in either direction. So, for example, if I'm at the point negative 1, negative 2, I can go up or I can go down. It's more like a line. But to fix that, we just say there's no arrows. So let me go and fix that real quickly here. That was at negative 2. All right, so let's go ahead and continue. If x is 0, my rule says the slope is going to be 0 minus 1. So negative 1, negative 1, negative 1, negative 1, negative 1. And if we're at 1, my slope is going to be 1 minus 1. So it's 0. So it's 0, 0, 0, 0, 0. Because remember, if I go over here, if x is negative 1, my slope is negative 1 minus 1, which is negative 2. If x is 1, my slope is 1 minus 1, which is 0. So let's go over here. What if x is 2? My slope is going to be 2 minus 1, which is positive 1. And if you notice, we turned a corner in our life here. 1, 1, 1. And if we let x be 3, our slope is 3 minus 1, which is 2. A little steeper. And this is what's called our slope field. So let's take a look. Well, what shape does this function look like? So that's the next question. What shape does the function look like in our slope field? And if you notice, it kind of looks like a parabola. Yeah. So if you said a parabola, that's pretty obvious. That's pretty easy. But let's take a look. Where do you think the vertex is at? It should be where the slope is 0, which is at x equals 1. That's where the slope is 0. So the next question is, well, how can we confirm this? Well, one way we confirm this, and we've already done this before, is if we solve the derivative. And this is what we've done before. We've done this before. So let's go ahead and take a look at reminder. How do we solve the derivative? If dy dx is x minus 1, we can say that the change in y, dy, is just x minus 1 dx. We've done this before, and we've integrated. So if I integrate the dy, we just get y. And if we integrate the x minus 1, we get x squared over 2 minus x plus c1. And if you notice, take a look right here, that square, that's telling us that our function is a parabola. So remember, the slope field gives us the shape of the graph. That's what the slope field gives us. And that shape is the function, which for us, we said was a parabola. Now, let's talk about that plus c for a second. Notice that there are many solutions. There's a lot of parabolas. I have a parabola here. Whoop, missed it. I have a parabola here. I have a parabola here. I have lots of different parabolas, many of them. So we say the slope field is not unique. So you might recall we talked about that earlier. When we have that plus c, it's telling us that the function is not unique. So, all right, so yeah, that's what that plus c right here means. It means that it's not unique for us. Right. Playing around my pen. Oh, come on, there we go. As a result, a slope field generates what we call a family of solutions. That's what this plus c is when we solve for that integral. When we solve for that integral, that plus c, that's what we're talking about, that not uniqueness. We're going to talk about how to make this unique in the next example here, and it's pretty easy to do. You got to figure it out really quickly. All right, so let's take a look at our next example. Oh, sorry, not next. So, so now we want to make the slope field for number 2. So before we go and do this, though, go ahead and I'm going to pause right here and go to the next video, okay? I'll see you then. Bye.